All right, I'm going to try to draw ourselves a motor here, and it might look sideways because I didn't make a JPEG for it before I printed all these lessons. So I didn't like impose a picture of the lesson. So I have to draw one, and so I'm going to do my best here. So first I'm going to draw the coil of wire here, and let's see if I can draw it with a thicker pen. So I'm going to try to draw it looks like this. So, like this. It looks like that. That. It's a rhombus, but that's fine. There we go. Actually, that's not bad. I'm actually pretty happy with that. And what we're going to put on each side is a big magnet. So I'm going to do this. I'm going to try to, this last one wasn't very good. Put there. And then I'm going to draw the same thing over here, but I'm going to try to draw it like, make sure it's beside it. You know what? This is not the worst thing I've ever drawn. Okay. Actually, that's not bad. Let's go back to the right size of the pen. Okay. Let's do back to this one, and then just extend these just a little longer. That's fine. All right. That ain't terrible. Okay. I'm going to call this magnet the north one here. I'm going to call this one the south magnet. Okay. Okay. Now that we can draw this, which way do the magnetic field lines go in this one? Which way do the magnetic field lines go from the big bar magnets? Yeah, they go to the right, from the north to the south. So just going to draw a few little arrows that look like this. Just like that. Just like that. That should do it. That looks right. Everything's fine. That's my magnetic field. I'm going to put that there. That's the magnetic field. So I'm going to try to keep all the magnetic field stuff in this like bluey gray color there. So that's the magnetic field. And let's put the current in this direction here. So we're going to supply current to this particular thing. And then obviously it will come back out this side. So at some point it's going to go, let's see if I can draw on top. It's going to go that way, and it's going to come that way through here. I'm going to draw one more magnetic field line because it makes it look cool over there. There we go. Okay, recording for us. So this is a motor. A motor is a device that converts electrical energy, we're giving it a current from a power source of some kind, and we're going to get mechanical energy out, usually a spin. It'll start with spinning, and if we want a motion that's not spinning, we have to hook up some machines to change the spinning motion into like a horizontal motion or some other linear motion that we want. But it's always some kind of then like machine step to change that motion. But the motor is always going to give us a spin. And so a motor is, to reference the last lesson, a generator in reverse. I think the easiest way to think of that is the difference between a wind turbine and a desk fan. A wind turbine gets the wind to push on it, makes the electricity. Desk fan gives electricity, makes wind. So it's just the same process in reverse. It's just easy to feel like it that way. So when the armature of the coil, okay, pop quiz, what does armature mean? Okay, armature means the coil bit, the movie bit, the thing that's going to move. So the armature is the thing that's going to move. When it spins, it will create magnetic flux. So it'll create magnetic flux because it will change the area the magnetic field sees through the coil. By spinning, it will see none, and then lots, then none, then lots, and so on. And that will create an EMF in it. Oops. MF. Totally nice printing. Okay, so what we're going to specifically talk about today is motors and something called back EMF. So what we're going to do with the back EMF is I have to do a lot of hand waving about this motor again. So we've drawn our beautiful motor. Which way is this motor going to spin? And I want you guys to get your hands out and figure out which direction this is going to spin. So we're following our right hand rule here, and I've got my magnetic field going that way. So here it's going to go down in this case. So back to where I'm here. So because, oops, this is recording. So we got the line here, and so magnetic field this way, we're going to get a down force. So here, we're going to get this down force on that bit, which means in reverse, on the other side, we're going to get an up force. That's not really easy to see there, but we're going to get this thing to spin in that way. So that's the way it's going to spin. Down on that side, up on the rightish side. This is kind of a perspective picture because we have to try to draw all three dimensions here on a simple page. That's where that is. Now, we have to figure out using our Lenz's law rules, which way does that spinning coil want to generate an EMF? So how do we figure out which way the EMF is going to be generated? You guys remember? Okay, so once this thing starts to move, it's going to have a velocity, right? So we have to figure out which way the velocity of the charges are going to go, right? So we use our right-hand rule for velocity and see which way that is. That again. So back EMF is induced in the current, or induced in the coil, induced in the coil of a motor. Of a motor. When it's operating. So when it's spinning, the spinning itself creates a current that's opposed to the supply current. So the motion it's making reduces that current. So really, we are reducing the voltage, which in turn reduces the current. So we want that to happen. So we have a new formula for this. And the title of this lesson is back EMF, because it's the EMF that's actually being generated here, and the current is the result of that. So our EMF back is equal to the EMF from the supply minus the current and resistance in the motor, in the coil. So this is our back EMF. And this is the supplied EMF, or the voltage from the source. So that's your 120 volt power socket, your 9 volt battery, whatever the power supplied to the motor is, it's reduced by, once that thing is spinning, it will create its own feedback loop. So, and it's, okay, well, we'll go into all these things because this is all going to be in the blanks down below. So the induced back EMF acts to oppose, because it's Lenz's law, so that's acts to oppose. Spelling, oppose. Acts to oppose, remember, that's Lenz's law. So it's always going to try to be like, nah, spinning is bad. We should try to change that. So we're going to get some opposition to the applied EMF, which will reduce the current. So the current is going to be less than we want, which is good. So for most things, this reduction isn't like a problem. It's generally what's designed into a motor. When a motor is designed to run like a power drill or like a blender or anything that you know is spinning at like a certain speed while it's working, this back EMF is 100% accounted for in the design of the machine, and that's good, basically. So it's proportional to the running speed. So the faster it goes, remember we used a velocity term, right? We used a velocity term to create our back EMF, and so it's proportional to the running speed. When a motor is turned on and starts up, there is no back EMF. So as it just starts to go, it has no speed yet, so there's no EMF generated at all. So we have this massive jump in current when the things start. And then once they run, the back EMF increases, and the current in the coil decreases. So when you start a motor, it gets a huge jump of current initially, and as the motor spins up, that current decreases to its like normal operating current, which it's expected to. If a motor is overloaded and slows down, think of like a power drill getting something really like stick, like the wood's getting tough or whatever, and it tries to slow down because it's working too hard. The back EMF decreases. Because the spin is less, the current will increase. And once you make a lot more current in a wire, that usually results in the motor heating up. And that's generally where the problems happen. So this is the general rule why motors can burn out. So if you overload a motor and it gets too hot, that's what burns out a motor theoretically. This is also what tends to cause, if you're using power equipment, drills, circuit saws, or whatever, and you're overloading those motors, the current jumps up, and that's what circuit breakers are testing for. The circuit breaker sees that increase in current and trips and turns off the machine to prevent damage, either in the circuit itself, because wires can only get so hot before they start fires, and they also trying to save the particular motors, whatever device you're using. You don't want those to burn out either. If there was no circuit breakers or fuses or those kind of things, an increase of that current would just break machines. Okay, so a nice, easy problem. The only tricky part is to not mix up any of the supply versus back EMFs. So switching those is probably the only mistakes you're going to make. Okay, so a DC motor, regular motor, connected to a 120 volt power supply, draws a current of 12 amps when it first starts up. At its normal operating speed, the motor draws 3 amps of current when it's running. Okay, find the resistance of the armature of the motor. So find the resistance in the physical motor itself. So we can use our only equation I've taught you for this chapter, or for this section. E back equals ES minus IR. You can probably see somewhere if you flip the S and the B, you can just add. That's how the subtraction signs works. Okay, so what we're going to look at right now is we're going to look at when it first starts up. when it first starts up, how much back EMF is there? None. So it's not really spinning yet. So as it first fires up, the spin hasn't created any back EMF yet. So we can pull this term away. And so we can say that the source voltage is going to be the total current and resistance here. So we can say these two, because the back EMF is 0, these two, source voltage and the current and resistance, are equal. We now basically just have Ohm's law. So the resistance in Ohm's law is equal to the voltage divided by the current. And the current in this case is the initial current in this case. So let's put a 0 down there for the initial, like initial conditions, velocity initial, etc. We know that the supply, oops, keep the S in there, the supply voltage is 120 volts, and the current draw initially is 12 amps. And so this is a nice, easy math problem. I didn't even need my calculator come out. The main resistance in the armature of this coil, this motor has a 10 ohm resistance. And resistance is like an inherent property of the physical motor itself, so it doesn't change. Once we've kind of calculated it and we can measure it, it doesn't change. It doesn't care how much voltage or current it gets. Once, like if it is 10 ohms, it's always 10 ohms. We can't change those. Okay, boring question here. What's the back EMF when the motor first starts off? None. 0 volts. And specifically because there's no speed. So with no speed, there's no force on the coil, so there's no push on the electrons from the speed, so there's no voltage at that point. Really should have done that question first. Don't know why that was listed. I'm just copying the book sometimes. That should really have been the first question, because the first question kind of depends on that being true. Okay. Maybe future me will reorder these questions for the next time. Not that it matters to you guys. All right. Find the back EMF when the motor is running at full speed. Okay. Another simple, straightforward question. E back is equal to E S. Yeah, I know they're not E's. They look like E's. They are I and R, and this is not my initial current. So I know the supply voltage is 120 volts. We know the running current measurement is 3 amps. And I know the resistance doesn't change because it's just a physical property of what the object is. I'm not going to put ohms in there. That would be inconsistent. So that's it. So the back EMF in this case is just 90. It's just 90. That is mathematically extremely simple. It's not an overly complicated stuff. So let me just write out our questions for today. New assigned questions are 194, hashtag 28 through 33, and that's it here. So